Okay, welcome to the last physics colloquium of the semester. It's my pleasure today to introduce Dr. Plazas, who's a Rubin operations scientist at SLAC and a community scientist with Rubin Observatory. He got his PhD at the University of Pennsylvania, studying systematic effective lensing, and continued on that path through postdoc positions at Brookhaven, then at Caltech JPL, and as research associate at Princeton. In addition to the science program, he has kept up and founded an impressive number of outreach and science communication activities to spread the joy of discovery and the importance of science, local and global. And today he's going to tell us about the biggest thing happening in cosmology right now, that is Rubin Observatory. Please take it away.
Okay. Thank you so much, Elizabeth. Thank you so much, everyone. My name is Andres Plazas Malagon, and it's my pleasure being here. It's my honor. So thank you, Elizabeth, for hosting me, and thank you, everyone. It's been great. It's been a pleasure talking with the students and everyone. And yeah, today I'm going to tell you a little bit about the Rubin Observatory and my work. I'm going to also talk about another survey called the Dark Energy Survey because I did my PhD on that. But yeah, I actually have an outline of the talk. I'm going to start talking about the Rubin Observatory. I'm going to tell you about the largest digital camera in the world, the LSST cam, and some of the work I've done to characterize it, show you some of the cool images, the first images, and motivate the science of why we're doing this. We're building this observatory. But then I'm going to focus on cosmology, which is my expertise in observational cosmology. I will do a review of our standard model of cosmology and how we can use gravitational lensing to learn about dark energy. And in particular, I'm going to show a few examples of some of the systematic errors characterization work that I've done. Then I'll talk about in the end about my work in the Rubin community science team. So the Rubin Observatory, this is an observatory we'll build in Chile, in Cerro Tololo. And we want to capture the cosmos with this observatory. We're going to conduct a survey that is called the Legacy Survey of Space and Time, the LSST. And we basically want to scan all the sky that we can see from that location for 10 years. And we're going to come back to the same position of the sky every 3 days. So in the end, we're going to have the largest digital camera in the world. This is what we call a photometric survey, which is actually we're going to observe all these celestial objects in different bands, different filters, ranging from the optical to the near infrared. And then you can see the filters, the 6 filters. But the three defining characteristics of this survey is that it's going to be an ultra-wide, ultra-high definition. It's going to be wide, it's going to be fast, and it's going to be like a deep survey of the sky. And it's supposed to revolutionize astrophysics. So I wanted to start with the pretty images. This is actually one of the 2 first images that we released last year. It's called the Cosmic Treasure Chest. And another one of the amazing images that we released last year is of the Trifid Nebula, and I think there's the Lagoon Nebula as well. And it's like, quoting one of my colleagues in the New York Times, he said, like, the whole thing all at the same time, because one of the big characteristics of this camera is the great field of view you'll see. And it all started, I'm going to start with a selected timeline for this project, and it started like 25 years ago with a slide, with a napkin, not a napkin, but with a slide of the design of something called the Dark Matter Telescope. And actually it was Tony Tyson and the current director of the Claris Mirror Lab here in Arizona, Roger Angel, and David Whitman, who came up with an idea of proposing a 3-mirror fast telescope in order to do a large survey of the sky, to use cosmology, to use weak lensing to learn about cosmology. Well, maybe in 2010, then the project was chosen as the highest priority from the ground, the astronomical community in the United States. In a report by the National Academy of Sciences, recommended it as the highest priority. And then we started construction in 2015. We put the first stone, then the project wasn't called the Dark Matter Telescope anymore, it was called the Large Synoptic Survey Telescope. But then in 2018, it was renamed by an act of Congress, actually, as the Vera C. Rubin Observatory. She was an American astronomer who provided the first convincing evidence for dark matter, looking at the rotation of course of galaxies. And actually she collaborated with an astronomer called Ken Ford, and they did many of their observations here in Arizona, the Lowell Observatory and Kitt Peak. And Vera Rubin was also well known for her advocacy for women in astronomy. And this is the first major US observatory named for a woman. Also, Arizona is amazing, as you know, in astronomy, and I wanted to say also that one of the biggest technological innovations of this project is the mirror. It's actually the main mirror is actually a combination of the primary and a tertiary mirror, and it was polished and finished here in the Richard Carey's mirror lab. It was cast in 2008, and then everything was finished in 2014, and it was shipped to Chile in 2019, and then brought to the summit in 2024. And it took 5 years because there was a pandemic in between, and it really was it was a rough time for everyone, including the Rubin Observatory. This is another nice picture of the mirror, and then this is another picture of the mirror that I like to show with people on top of it to show a scale of it. It's an 8.4 meter main diameter, and the key of this is that it will allow us to it will allow us to survey the whole sky at a very fast speed, and the speed is proportional to something that is called the ATNU, or the throughput, which is like a number that you get to multiply the effective mirror area by the field of view that you get, and then you get a number that is the largest number for all telescopes that we've ever built. So we're going to put these mirrors in the telescope that is called the Simony Survey Telescope. So sometimes it can get confusing, right? It's not called anymore the LSST, the Large Synoptic Survey Telescope, but the observatory is the Rubin Observatory. The telescope is called the Simony Survey Telescope, and now we also have the LSST camera. So this is the largest digital camera in the world with 3,200 megapixels, with a field of view, or with a diameter of field of view of 3.5 degrees, which is basically you can feel 40 full moons in just one snap, in one shot, and this is going to be fundamental to survey the whole sky, and then every 3 days. So as I mentioned, we're going to have 6 filters going from the ultraviolet to the near infrared. And at the heart of the camera, we have the detectors, which are called charge-coupled devices. And I'm going to be talking a little bit about these digital detectors and how the errors that come from this detector propagate into science. But these detectors, each one, they have about 60 million pixels. Each detector is divided in 16 channels, and they're grouped in electronic rats of 9 CCDs. So these are called 9 rats. Each one of these rats is like an individual camera. And the camera, everything was built as SLAC within 10 years with a very high precision. It was like a very high feature of engineering making this camera. It actually holds 2 Guinness records as the camera with the highest resolution in the world. And one of the optical mirrors, the largest one of 1.6 meters, is the optical lenses is the largest optical lens in the world. So this is another nice picture of the camera in a clean room and at SLAC. And then this is again the focal plane, which I also wanted to shout out again to Arizona, because the CCDs, the focal plane, they come from 2 companies. One of them is called Teledyne. The other manufacturer is actually the Imaging Technology Laboratory here in Arizona, the ITL CCDs. So yeah, that's pretty cool as well, and that's why I'm also very excited to be giving this colloquium here today. So when you have a camera like this, you need to do a lot of tests, electro-optical. It's called electro-optical testing. A lot of my work also has to do with writing the software in order to characterize these properties. And when you have a digital device like a CCD, you can illuminate it with uniform light, and then you assume in Poissonian statistics, you get something called the photon transfer curve, which is like the variance versus the mean of that. And then the point of that is a very important curve when you're characterizing CCDs, and then you get parameters such as the electronic grid noise. You get the conversion gain from digital units or analog to digital units into electrons, or for example, the capacity of each pixel, what is called the full well, which is about like 100,000 electrons per pixel. So this is just an example of the type of characterization that we do.
Question?
Yes, yes.
Can you go back?
Absolutely, yes.
So what's the matter with the gain that it drops off so sharply or towards the center?
Why do we have like two types of gains? Or?
Yeah, exactly.
So in general, as this is correlated with the two families of detectors that we have. When you actually look at the histograms, they're not quite different, the gains, but because they come from two different manufacturers and two different families, we do tend to find different types of histograms and characteristics for each one. So here, I guess the scale is hard to see. That actually the mean value is not that different, but every time, this is very, you're right, every time you do one of these plots, you tend to see the differentiation between the two families of detectors. And every time I have a student analyzing this focal plane, I say, did you separate by the detector types and all that? So yeah, that's a very good point. And this CCD, so the charge-coupled device, it revolutionized astronomy. Of course, it was invented in the 70s. The people who invented it got the Nobel Prize in 2009. And one of the first cameras, or mosaic cameras of CCDs, when we were start thinking about putting a lot of CCDs to serve the sky, that was that one in the upper left there. It was called the Big Throughput Camera. It was actually made by my PhD advisor, Gary Bernstein, and then also Tony Tyson that I mentioned. So sometimes people call it the Bernstein-Tyson camera. But the point is that it's a historical instrument that is actually at the Smithsonian Museum in DC. And the CCDs, but then the CCDs that we have for the LSST camera, they belong to a different type of CCDs that are called like thick, fully depleted, back-illuminated CCDs. And it sounds like a mouthful, but I guess I want to focus on the thick part. What do we mean by thick? CCDs like in another camera, like for example, the camera for something called the Sloan Digital Sky Survey, which is in the second picture right there, one of the first detailed surveys of the skies. They usually have like a thickness of like 15 microns. But then when we started thinking about using this detector, the CCDs for doing cosmology, we wanted to be very sensitive to the red because of the expansion of the universe, and spoiler alert, the universe is expanding. Objects are actually red-shifted, so their spectra is shifted towards the red. So because of the wavelength, the length absorbance of the light in silicon, you need to actually have like a thick CCD, which in this case of the SST camera is about 100 microns. So I actually, they also, you can see the efficiency curves, you can see there on the right, on the left part, on the lower right. The blue one is showing us how these devices have like a very high efficiency in the near infrared part in order to be able to do more cosmology with, this type of devices. Then in the lower part, the lower left, there's a camera called, well, the upper part is called the Hyper Supreme camera. Then you have the LSST camera on the lower left, and then on the right, we have the dark energy camera that was built. It was also put in an observatory close to where Rubin is, called Cerro Tololo. It has 500 megapixels, and I actually started working on that camera about 20 years ago. I was preparing this talk, I found these very old pictures of me as an undergrad doing characterization of these devices at Fermilab, where the camera was being built. So this is like the first slide that we had with the detector, with the LSST camera. And then if you look closely, it's just full of donuts. So what's going on? That means actually that the telescope is out of focus. So you use something called the active optic system, which you use like actuators to change the shape of the mirrors, and then you like do feedback, open and close loops in order to put the thing in focus. And then voila, you're more in focus here on the left. If you look very closely, the detectors that are at the very corners, they still have donuts, and that's on purpose because they're actually off the focal plane, and those are the ones that you use to focus the telescope usually during the survey. Okay, but then once you apply the magic of the active optic system, then you get this image on the left here, which still doesn't look quite nice because this is a raw image. And I'm not going to go, this is like a whole different talk as well. But a lot of the work that I did when I started working with Rubin was writing algorithms in the LSST science pipelines for something that is called instrument signature removal, which is actually doing that, which is a long change of steps to correct for everything that the detector is actually putting into the image. and just put the flowchart here, but you correct for things like nonlinearity, charge transfer, the gains, defects in the detectors, etc., etc. But then once you do the magic of ISR, of instrument signature removal, then you get something that looks nicer. I guess it's not as super cool, but it's like our colleagues were very, very excited when we actually saw this image in Cerro Pachon back in April. So then we did a press release in June of 2025, and that's me. I happened to be in St. Louis, in Washington University in St. Louis, and then I did an event, an outreach event, holding my 2-year-old, and that was a lot of fun. And then this is one of the movies actually of the first images that we published, and I wanted to share with you because it's pretty cool. And I encourage you to go to rubinobservatory.org, and you're gonna find an app. I guess there is a lot, but go to the app, and then you can actually spend a lot of time. I spent a lot of time zooming in, zooming out. There is a version of this that has sonification, which if you pass your cursor, it's gonna produce different sounds. But here you can start appreciating the galaxy density, how you're going deeper, how you can get more details in such a way that we have not had before with another type of instrument and survey. And yeah, we're gonna do that for the whole sky. So here, this sequence of images of one part of this the first light image is showing all the instruments. This is one from Palomar in 1994 of this particular part of the Virgo group. Then we have the Longitude Sky Service that I already mentioned in 2000, one of the pioneers of this galaxy survey, the Sky Service. And then we have another one in Hawaii called Pan Stars. So then you can actually see the transformational quality that we're getting with the LSST. So with this, with the LSST and with Rubin, we wanna revolutionize astrophysics in mainly 4 science areas. The 4 science pillars of the LSST are gonna be the study of the Milky Way, the structure and formation. Also, we're gonna do a census of the solar system, and it actually has allowed us to discover already thousands of asteroids and even interstellar objects like 3I Atlas. And it also will allow us to detect objects that might hit the Earth and are potentially dangerous for the Earth. And then also the changing sky, any changes, astronomical phenomena that change, like supernovae or AGNs or other types of astronomical objects that change. And that's why we go back every 3 days to the same part of the sky to see what changed. And that's what is called transient science. But as well, we want to learn about dark matter and dark energy, and that's cosmology. And I'm going to focus on that now. So for that, I'm going to very briefly go through a primer, I guess, of cosmology, and with cosmology and the history of the universe in a few minutes. In cosmology, we want to study the universe as a whole, and the universe is 13.8 billion years. At some point, very, very, very early at the beginning, there was the period of the Big Bang, or everything was very hot and very dense. Just after a fraction of the Big Bang, there was a period of accelerated expansion. It's called inflation, that actually made the universe super flat, and it also amplified, it provided the densities for the structure formation that we see today, like these quantum fluctuations that were happening there, where it produced inflation, the seeds of these fluctuations. But then at the beginning, still, the first 3 seconds, we still had like a plasma of everything that was together, like ordinary matter, photons, dark matter. But then at some point, as the universe expanded and cooled, the photons decoupled from that plasma, and then we got something that is called the cosmic microwave background. Then just fast forwarding, at some point galaxies started forming, and they started forming what is called the cosmic wave, or structure formation through what is called gravitational stability. So gravity was just like doing its work and producing this cosmic web. But then the universe was expanding, and then about 4 to 5 billion years ago, the universe started actually expanding in an accelerated way. So this is a framework that is based on observations like the expansion of the universe, the CMB, the abundance of early elements. And it has this observation, of course, of the accelerated expansion of the universe. So we actually, this was discovered in 1998, and the teams who discovered that got the Nobel Prize in 2011. We don't know the physical nature of whatever is causing the acceleration of the universe. Assuming general relativity, which is what we assume in cosmology, then you need to introduce a new component of the universe that we call dark energy. And the simplest model for that is something that is whose energy density is constant in time and doesn't change as the universe expands. And that is called the cosmological constant, and that's what is that Greek letter lambda represents that there. But then in this model, the standard cosmological model that explains many of the observations in cosmology also invokes a type of dark matter called dark matter. And this assumes, as I said, general relativity in a homogeneous and flat universe. So we have a standard cosmological model of 6 parameters from which we can derive something like the amount of clumpiness of dark matter, the amount of dark energy, the expansion rate that explains observations. And today, about 95% of the universe is dark energy plus dark matter, and the rest is what we call ordinary or baryonic matter. So this is okay, it's good that we can explain a lot of observations, but it's a model that calls for non-components beyond the standard model of particle physics. So we're looking for deviations. We're looking for like how can we test this model. One possibility is that maybe it's not a cosmological constant, maybe something that is different from a cosmological constant. So in that case, we can define, or it's a cosmological constant with a different value. From lambda. So we can define something like an equation state, which is the ratio between the pressure and the matter density of this dark energy. And that's what we call with that parameter W. It could also be that the parameter W changes with time, so we can do a parameterization of that as a function of redshift or cosmic time. And then recently, there have been projects like the dark energy spectroscopic instrument, similar to DES, but not DESI, that have shown that there are hints maybe that dark energy might be changing in time, but this is not fully there. It's not conclusive. So, but it's very interesting as well. And there are other observations that tells us that some of the cosmological parameters that we derived, like from the early universe, for example, we find different values for the amplitude of matter fluctuations in the early versus the late universe, or different values for the expansion rate with different methods. So these are hints that are showing us that the model needs to be updated. So one way in which we can learn about dark energy is using gravitational lensing, and gravitational lensing is the bending of light by any distribution of matter and energy. But then in gravitational lensing, you have different types of gravitational lensing. So one type is what is called strong lensing, in which you have the observer, you have like a lens, which is a distribution of mass, a galaxy, a cluster of galaxies, and in the background, far away, you have, in this case, in the strong lensing here, you have another galaxy that is blue, and the alignment, this depends on the geometrical alignment between the lens, the observer, and the source. And when the alignment is perfect, you get a ring, it's called the Einstein ring. In this case, it's almost a ring. You can have this shear, and this, you can see it with just one galaxy. But then you can have another opportunity to look at a galaxy cluster. Close to the center of the galaxy cluster, you start finding like a tangential shear of the strong lens, and you can see it with your eyes. As you get closer, as you get away from the center, you still have distortion of the galaxies, but as you start entering into a regime that is called weak gravitational lensing. And this signal starts to be of the order of about 1 or 10%. But the technique that will allow us to study the expansion history of the universe and the broader structure of the universe is the weak lensing of the large-scale structure of the universe, or the weak lensing of the cosmic web. And that's what we call cosmic shear. And that lensing signal is of the order of 0.1%. And that's the signal we're after that will tell us about how dark matter is distributed in the universe in different moments in cosmic history, and how that dark matter distribution changes with time. So this cartoon is also useful to learn a little bit about what the gravitational lensing is doing. If galaxies had intrinsic shapes that were circular, and then you put a lens, then you got ellipses, and then you measure the ellipticity, and then you're done, because that's the shear, that's the lensing signal. But the true background has the galaxies have intrinsic shapes. So it is more challenging. But in the end, this is exactly what we want to do. We want to measure the shapes of galaxies. We want to produce what we call a shape catalog. And then we want to start calculating what we call summary statistics or correlation functions between those that correlate with the structure, because that's telling us about dark matter. So we actually do a two-point correlation function of the shear of different galaxies. This is what we have on the left here. But then you start adding information from other types of correlation functions. So first you do the correlation function of the shear signal, but you can correlate the position of the galaxies that are in between as well. This is like a galaxy clustering. And then you can do the combination of the two, which you correlate the position of the galaxies, and then you look at the tangential shear around those galaxies. And then these correlation functions, they're most sensitive to cosmological parameters, in particular related to the matter density and the amplitude of the completeness of the density fluctuation. So maybe a little bit technical here, the equation, but the point is that these correlation functions are related to the power spectrum of the dark matter density field, which is what we want to sample. We have a density field of dark matter, and then this summary statistics is going to help us find information about that. And we do this in different redshift bins in the history of the universe. And then this is a movie that shows us the type of measurement that we do. We have the data vector in different bins, different correlation functions, and then as you change, in this particular case, you're changing one cosmological parameter, then you can start feeding for the cosmological parameters. That line is the prediction that we get from general relativity. And I guess that I also forgot to mention that dark energy is how I presented it, is assuming general relativity, but you could also have the alternative that we need to modify general relativity on cosmic scales. And these measurements are also sensitive to that. But then, I mean, it's usually not that easy, I guess. As I said, you need to measure the galaxy shape. And then here, this cartoon is showing us exactly a little bit the challenge of what we need to do. If you start at the bottom left and you have like a galaxy that has an intrinsic shape that is unknown, then you have your signal, which is exaggerated here, but as I told you, it's like 0.1%. Then your photon comes to the atmosphere, the telescope, like create a convolution, then the photon lands in a detector, and then the detector also has noise, so then you need to come from the image on the right back to the shear. And that's the challenge, that's the inverse problem. How do we deal with that? We do have sources with known shape, and those are stars. Those are point sources. And in a perfect world, if we have a point source, then we will get a point in our detector. But of course, that doesn't happen. However, that's telling us that that is called the point spread function, how your point source looks in your detector, and it's finding information of all that convolution from the atmosphere, the detector, and everything. Here, if we think a little bit about it, then we say, okay, we measure the PSI from the stars here, and if we decompose in the galaxy here, and we get the shear, and we're done. But doing that, that's an interval already, is telling you that you have to interpolate to another part of your detector that introduces errors. And also your stars and your galaxies are going to have different spectral energy distributions. That's another example of how things can and do go wrong. So a lot of the work now is focused on doing systematics control. Because why? Once we start, I was mentioning that with the strong lensing, you can see it with one galaxy, and then with weak lensing and cosmic shear, it's actually impossible to see it with just one galaxy. But because we have that shape noise, that intrinsic shape of the galaxies, and but you can beat down that shape noise if you have hundreds of millions of galaxies, which is that's part of the reason why we have these wide galaxy surveys like the Dark Energy Survey and the LSST. And then you're at a point in which you're not limited anymore by statistical errors. You start being limited by what's called systematic errors, which, as you know, don't go away with all as long as it doesn't matter if you have a lot of data. And then this was identified even like 20 years ago. There was a report by something called the Dark Energy Task Force report that identified weak lensing as a very promising technique to learn about dark energy if we were able to control systematic errors. So these systematic errors come from point spread function measurement, modeling, interpolation. And then also another way of quantifying these systematic errors is with this equation, linear equation that we have there, in which your true shear is actually modeled by a multiplicative term, and then you also can have an additive term that mimics the signal that you want to observe. Then also this plot that shows us that's here from a paper of 20 years ago tells us like you can put constraints on how small your multiplicative and additive terms need to be in order not to degrade the precision of your cosmological parameters. So in the case of LSST, and what is called stage 4, this terminology of stage 4 was introduced by this same report 20 years ago. Stage 3 are projects like DES that were about to start back in the time, and stage 4 is something like LSST and DESI, which was the future back then. So, but this time you need to have a multiplicative error less than that. So now I'm gonna talk a little bit about some of the detector effects in which I have worked that are related to PSF modeling. But this is, I wanted also to show a little bit like an equation of error propagation in which you can see how a fractional error in the size of the PSF, that's that delta T. T is the size of your PSF. Delta T over T is like a fractional error, and then you also have an error in the ellipticity of the PSF, but that propagates into a systematic error for a galaxy shape. And then this is the type of things that we're doing right now. You can see that map on the right, in which you do a PSF model, and then usually you do like a polynomial that takes care of optics and large scale, but then you look at the residuals, that's the important thing. And then you keep looking at the residuals, and then you start seeing correlations with the vignetting, you start seeing correlations with the different types of CCDs. And actually, if you look at the CCDs that are closer to the periphery, you see like some blobs, and then it gets deep. You can go into a really deep rabbit hole, but then we found out that those are, for example, correlated to the height differences of the CCDs in the focal plane. So once you take that into account, then you can take those residuals out and then bring them down the requirements. And then the equation in the bottom is just an example of how you can just propagate that shear equation with the linear multiplicative and additive error. You can propagate that into a correlation function. And it gives you an idea of how this can bias the correlation functions that you want to measure. So one of the first systematic errors that I studied back like 14 years ago has to do with the atmosphere, something called differential chromatic refraction. And this is an effect in which the atmosphere acts as a prism, and different colors are refracted by different amounts, and more for blue. And that introduces a stretch of the image along the zenith direction that depends on the source of spectral energy distribution and could mimic a weak lensing signal. That's that R term that is there. And we show that this is something that is, for the first time, that is not negligible for stage 3 and stage 4 surveys. So you can that stretching induces like a big term, like a convolution that is going to mimic your weak lensing signal. So we measured that and we compared it with the requirements for DES and LSST, which are those gray bands here in the center. And we showed that in the blue as expected, for different types of stars and galaxies, this is something that needs to be taken into account, or that you need to be careful if you want to include G band or blue bands into your analysis. So we included that in DES, and right now we're studying the impact of that in the that is going to have for LSST, and then you can see that other plot is showing the comparative, the LSST, the correlation function that you get, the contribution to the correlation function that you get from statistical errors as a black line. If you don't correct for this DCR, then you get the blue point, the green points. If you correct for DCR, then you get the red points. That you still see that even at larger scales, there's still some work to do with the current correction that we have. But that's one example of a systematic error I've worked on. And I wanted to mention two other types of systematic errors coming from the detectors themselves. And coming back to these fully depleted, back-illuminated CCDs, you can think of them actually as like skyscrapers, like here, like the DCAM CCDs, they're 250 microns long. But the LSST CAM CCDs are 100 microns, but the size of the pixel is 10 microns. So it's like a ratio of 1 to 10. And what's happening is that normally you have an electric field in the back of the CCD that is going to transfer your charge that is photogenerated by the photoelectric effect. It transfers it to a potential at the front of the of the CCD, and then you start doing your charge transfer, and then you read it. But this type of CCDs could also have spurious or other type of electric fields that I call them, we call them transverse electric fields, that could actually start pushing your charge around from one pixel to the other. And that's going to be a problem, because that means that if you thought that your galaxy was here, but it's actually, you measure it here, that induces an error in what we call astrometry. Well, it also induces an error in photometry, and then again, that propagates into PSF modeling and shear measurement. So you can have different types of sources for these transverse electric fields. You can have space charges in your detector, you can have impurities in the detector, or even close to the edge of the detector, you can have the formations of the electric field. So one example of impurities in the detector is this effect that we call the tree rings, which actually, when you look at a CCD with a uniform light, in a perfect world, then every pixel, if you illuminated the CCD with uniform light, every pixel should have the same amount of light. But then you say, okay, then this pixel didn't get 100, this pixel got 80, I don't know, in whatever units, 80%. Then you say, okay, that's fine, that's my correction function. It's called the correction factor. It's called efficiency. And that's what your flat field is supposed to correct for. But when you have something that is actually moving the charge around, like these tree rings, you cannot just correct like this, but correct for it like that. So back in 2014, using on-sky measurements, we demonstrated for the first time that these were actually effects that cause the charge to be moved around. And this is actually that map here, that big map here of the dark energy camera that has what we call the astrometric residuals. After we correct for a lot of other things that could cause astrometry, like atmosphere, optics, you still see these correlations with the tree rings, and it shows us that the charge was being moved around. So we developed a method in which we measured the profiles of these tree rings in flat fields, and we were able to predict an astrometric signal from that. We were able to show that due to the conversion depth of light in the silicon, the blue light actually should have higher amplitude because they get converted closer to the back of the CCD, so they transfer during more time towards the front of the CCD where they're being collected. So the transverse electric field has more time to deviate the charge. So we actually saw that, and then in such a way, the red photons, they shouldn't have the same amplitude as well. So we were able to identify that chromatic dependence, and we put that in the astrometric solution for DES. And then right now I'm doing the same, but for LSST CAM, I guess the eternal return of the same thing, I guess. But I mean, it's cool. Now it's just now we have 189 CCDs, so it's on another level. And then the other effect that I wanted to tell you about is called the brighter, farther effect. And this is an example of a space charge effects in which once you start accumulating charge in a given pixel, the charge that is already there being accumulated starts generating its own electric field. So new charge starts moving gets moved by that new electric transverse field into a different pixel. And it's the same story. The charge is being moved around in pixels, and that's not good. And then that means that the PSF size increases with flux, hence the colloquial name, brighter, farther effect. You can model this as the effective area of the pixels being changed as the charge accumulates. It gets deviated from a perfect grid, and it changes. You can come up with a phenomenological model in which you can get the boundary displacements as a function of the charge in each pixel, and then put the charge back where it should have been. And we did that for DES, that it corrected for about 90% of the effect, and that was good enough for DES. Even in that case, this other example shows that this is an example of errors in the size of the PSF and the electricity of the PSF as a function of magnitude, and how you still had to throw away some of the bright PSF stars that you would use for PSF modeling because of this effect. So this 90% effect correction was good enough for LSST, I'm sorry, for DES, but it wasn't good enough for LSST given the requirements. So we needed to come out with a different solution. I didn't come out with a solution. It was a group in France, but You can see this in this plot on the right. You can see the red points. So we have here again the fractional size of the PSF. That's a quantity that we're looking at always as a function of signal. If you don't correct for this effect, then you have something that goes beyond the requirements for LSST, which are the green bands for year 1 and year 10. Then we implemented a correction that is similar to the correction that we did for DES. This is what is the blue points. Is still not there enough, but then we implemented another correction proposed by this group in France, in which they did a little bit more careful modeling, electrostatic modeling of the problem, using Gauss's theorem in order to be able to measure that displacement of the boundaries of the pixels and correct for it. And that is actually getting us there for year 1, but we still have work to do for year 10. And we're there, but we're there one step at a time. So I wanted to make a parenthesis to go to space, because actually a lot of the work that I did at Caltech had to do with studying this brighter, farther effect, but in near-infrared detectors. And they're different, they have different architecture, it's a different type of material. They're actually mercury, cadmium, and telluride. But you can also find this type of effect we were able to measure that with a projector that we had at Caltech, in which we put like a grid of stars, and we were able to measure how the charge was being redistributed for like a central part of the stars into the surrounding area, which is what you see in that plot. That plot, I think the blue is the charge in the center. No, the red is the charge that gets lost in the center, and the blue is the sum of the surrounding pixels, and they cancel out more or less. So, but it's an indication of the existence of the detector. So I'm not going to go a lot into that, but I want to show that we did a measurement of this for near-infrared detectors in the Hubble Space Telescope, also with a Euclid near-infrared detector, and then recently for a Roman near-infrared detector. And it will have impact for wind lensing and for other science applications. I wasn't thinking about JWST, but now a lot of the papers from the JWST are actually citing this paper because they need to take this into account as well. So coming back to the ground, and then coming back to putting everything in context. So I told you about some of the technical work that I've done with systematic effects. And that, I wanted to show this chart about this is our goal, to go from pixels to cosmology. And then a lot of these effects go into that little box that is called PSF modeling. Some of the bright matter effect, that was one of the boxes in the instrumental signature removal chart that I showed at the beginning. The DCR, the chromatic refraction, differential chromatic refraction, and the 3 rings and stuff like that goes into the astrometric solution, which is the map between pixels and the sky. And that goes all into the PSF modeling, but that's just, as you can see, it's a complex problem. There's a work of more than 100 scientists, in which you start with your catalog. This is for DES. We started identifying about 600 million objects or more. Then you need to do your PSF modeling, produce a lensing source catalog. In the end, we ended up with about 150 million sources. But then you need to take into account other stuff like the blending of sources. You need to take into account the redshift, that's a big systematic as well. And a lot of the work then goes into doing the Bayesian modeling, the modeling of all this data in order to produce cosmological parameters. And a lot of the group here in Arizona, like Elizabeth and team, are involved a lot in this as well. So then in the end, that's putting everything in context in order to get the cosmological parameters. And then after like 20 years, we recently showed some of the first cosmological results from DES, and it was an emotional moment for me. I guess I wasn't super involved in this because I was involved in other, in Rubin and other stuff, but I did some of that early work, and it's pretty cool. So we produced the largest weak lensing catalog today. In Lambda CDS, we don't find significant evidence for inconsistency between the DES and the CMB and LA Universe probe for DES and other complementary probes. We do find a lower systematic value of that. This S8 is a combination of the amount of dark matter and the clumpiness of dark matter. So, but it's not super statistically significant. And then also one thing that I didn't mention, but this is the first time in which we combine 4 plus of dark energy. I've only talked about weak lensing, but I already started introducing how combining things in such a way that the sum is going to be greater than the parts. We combine correlation functions, and there's like this 3 times 2 point analysis. But you can also combine different probes. So weak lensing of the large scale structure is one probe. You have other types of probes like supernovae or something called variant acoustic oscillation or dimensional galaxy clusters. And with DES, we have different probes with different systematics that will increase the power, the constraining cosmological power of the project. So in the end, we got constraints similar to what the CMB gives us, but we constrain in the end equation a state of dark energy to about 4%, but we find something that is consistent with lambda CDM. But well, all this systematic control was able to enable these cosmological results and will enable LSST. LSST will produce about 1 order of magnitude of more galaxies of the order of 1 billion or more for doing weak lensing. And then with lensing of the large scale structure, there is a science collaboration within the LSST called the Dark Energy Science Collaboration. Anybody in the United States can join if you're interested. And then it will definitely, of course, increase. It will combine again the different correlation functions and increase the constraining power. And it will also, in addition of using those 4 probes that I mentioned, it will use strong lensing as an extra 5th probe in order to produce constraints on the equation of states of dark energy. And right now, we want to answer the question: is dark energy changing with time or not? So it's very, very exciting times. But I wanted to finish, I guess, and leave some time for questions. I wanted to finish with the work that we're doing in the Rubin community science team, because we have an amazing instrument, but in the end, it's the community, it is you who are going to do the science, and we want to put the community at the center of this. And we have a team in which we support anybody who wants to do data with the LSST in order to maximize the data that we do with the LSST, to maximize the science impact that we do with the LSST. You have data rights, you can get an account right now. Don't take that for granted, because in the past, other projects like DES, for example, there were only certain institutions. Here, anybody in the US, if you're doing research in the institution, you can get an account, and right now you can ask me more about it, but right now we do have some Rubin data that we took with what we call a commissioning camera, which is like a camera that had only 9 CCDs, it's still like 140 million pixels. This is called like data preview 1. You can still, it's not a lot of area, but you can still start playing with the data, with the Rubin data. There's 7 fields for different science cases. For cosmology, we have some extragalactic fields that overlap with other telescopes like Euclid. And I even started writing a paper with a colleague that I met in a conference in Mexico last year. It's like about doing a star galaxy separation with machine learning techniques with DP1. So you can even do science with it. And I know other people are doing science with this. I wanted to mention that in addition to, I talked a lot about what we call static science, but I did mention the transient science. And that part of LSST is what is called the prompt products, in which you have like a template of the sky, then you have your science image, and then you want to see what changed. And we're gonna get about every night. We already started getting what we call these alerts, about 7 million alerts per night, that they don't get distributed to people directly. They get distributed to like intermediary brokers, and you can subscribe to these brokers and then get the alerts in order to do science if you're interested in that. But I just wanted to mention that as well. You can ask me more details if you want. And just to finalize the last three images, I wanted to show some actually early science that we did with data preview 1, which we measured the weak lensing signal around a galaxy cluster. We were able to identify the tangential shear around a galaxy cluster with 3 different shear methods. With that's like it's a big feature. It's good. It was something that is not non-trivial to do. And then with this data preview 1, but then in a few months, we're going to have the next data preview that is going to have about 3,000 square degrees, and that's really sizable. I guess I didn't mention this, but the dark energy survey is about 5,000 square degrees. Rubin is going to be the whole thing, the LSST, but here we're going to have like a very large chunk of the sky. For this data preview 2 that is going to be released in a few months, between July and September. So I do encourage people to start using Rubin data. And then also the other thing that I wanted to mention, that we have the combined power of multi-probes. We also have the combined power of multiple experiments in different wavelengths, because Rubin is not happening in isolation. There are other projects from space, like Spherix, the Roman Space Telescope, Euclid, then other CMB projects planned in the future, and then people are start thinking about these kind of things, how to do, for example, joint processes or combining all this to maximize the constraining power of science, in particular cosmology. Just to finalize, I wanted to also mention some of the accessibility work that we've done in the community science team, because we want to remove barriers for research. So we've done some research into looking into universal design, looking, for example, alt test into our documentation. Then in the center, we have like a guide for writing our tutorials in the community science team. For example, looking at different colorblind friendly plots. We organized what we call a Jupyter Notebook Accessibility Hackathon, led by colleagues from the Space Telescope Science Institute. And then we commissioned experts in accessibility, and we paid them to do an accessibility evaluation report on the Rubin Science platform. And then we got a report, and we're implementing the recommendations. And also another topic I'm interested in is in removing barriers of language. And we got a small grant to do like a literature research to produce some recommendations to overcome language barriers in the Rubin Observatory for people who use English as an additional language. And then another thing that also I'm passionate is mentoring and research and outreach, as Elizabeth mentioned, but I don't have a slide on that. But there is one thing that I want to do is to increase the participation of LSST and to promote the development of astronomy in Colombia. So we have a program, a virtual program, an undergrad virtual program of 10 weeks in which we pair students in Colombia with researchers of other parts of the world. And I've talked to my friends in the LSST and tell them, hey, you want to mentor a student? Volunteer, sorry, I can't pay you. But we've had some interesting projects, for example, about doing photometry for SLAC, Starlink, satellites, or doing like a deep learning, using machine learning for point square function, or doing some cosmological tests, the software that we use for the correlation functions. And also I had once the students do some reports of the LSST camera. And then another thing is that thinking about using Rubin data in the classroom. The Rubin Science platform is not quite designed for teaching, but in principle, your whole classroom could have accounts and the RSP and do something like that. We did something maybe not similar, but I'm an associate in the physics department at Harvard, and we used a little bit some of the Rubin data to integrate it in collab labs with the use of generative AI, and it was a way of getting undergrads into using Rubin data and also with generative AI, so we can talk about that later. This is just for reference. Go to rubinobservatory.org. Everything is there for scientists. And yeah, just a reminder that this is like a team effort, a lot of people. And this, let me finalize with some nice pictures of myself with Rubin. And actually, I have a picture there of my time at BCAM observing in Tololo. And the picture on the right, it was actually the first time I observed ever. It was at Kitt Peak. So I just wanted to show that because it was very cool. Thank you.
We have time for a few questions.
Hi, guys. Great talk. I was wondering, when you increase the number of galaxies with LSST for measuring with lensing and feeding everything by the numbers, do you have to do a sample selection of those increased number of galaxies that into the 90s that I saw in the plot? Like, do you have to filter or do a selection of those galaxies, leave someone out in order to insert them, because they don't meet certain criteria?
Yes. We usually, actually, LSST is going to measure of the order of 20 billion galaxies, but then for lensing, you end up with, you need to do a lot of quality cuts, and I didn't mention there's masking, there's like a lot of things that you have to leave out. And yes, you end up with something smaller. With DES, I mentioned initially we had like 600 million objects, but for the shape measurement, you end up with like 150 only, I guess. But yes, we need to do that.
Now, brighter factor and other effects in CCDs. Is that something only astronomers care about? The physics of it sounds like pretty universal, and other people using these effectors might also be interested. Do you know?
Yeah, as in physics, you know how to do approximations, I guess. You need to ask yourself, what's your signal? And do I care about this effect or not? So this is for a long time, these effects are like of 1% of the order of 1%. But after a signal that is like 0.1% of galaxies, and then you do your error calculation, and then you realize that this is a big part of the error budget. So if maybe you're doing an experiment with these detectors, and then you ask yourself, what's your signal, and what's the noise, the usual. Yeah, so it might be relevant, or maybe not.
I want to ask a question regarding the cosmic shear analysis using the LSST data. Like, from the quality of the LSST data of the benzene catalog, are there any like significant changes that we should consider about systematic modeling compared to like stage 3 surveys, like in aspects like photo Z errors or like shear multiplicative bias or anything? Like, are there any, like, do we need any significant change of the modeling method or like the handling of the system methods?
Yes, and that's actually, we're talking a lot about with the people who did all this stage 3 analysis, and it's going to be a lot of them, the same people doing the LSST. One example I already mentioned, the brighter fatter effect. I guess the correction that we have right now is good enough for year 1 requirements, but we have to come up with something different for year 10. And the same with all the other systematics. One that also comes to my mind is what is called blending, because we're going to have such high density of galaxies that like 40% of the objects are going to be blended, and that's going to be a big problem. That's something that comes to my mind right now, but yes, in terms of updating methods, and that's a discussion that is happening right now with the Dark Energy Science Collaboration. Like, what kind of methods do we need to update? Do we need new methods? Can we use the same one? Or is it going to scale? Because this is actually going to be on a different type of scale of area of numbers. So yeah, there's more to do.
One big question is about this CCD. So DES, I think at some point 2 of them died, went away, and there was a discussion whether to open it up and replace them or not.
Yes.
Are there concerns about similar effects in LSST? And if so, is there a plan what to do if one of them basically goes away?
Yeah. Maybe you didn't see it, but actually 360 already failed. So some of the plots, you can see some black areas there. I don't know if I'm going to show that too much, but I did. No, they recovered 2. Actually, here, there you go. They recovered 2, but then there was one that wasn't recovered. I don't know exactly what happened, because I wasn't there, but that white square there, that's a CCD that's there, and then these are matter of cost risk, you know. So this is fine, you know, for now. I don't know if there's like a threshold of minimum number of CCDs that will prompt people to stop and open the thing and fix, you know, like in the camp, yeah.
All right, with that, let's thank Anders again.